Okay, so our third speaker this morning is Ardizzoni, who's going to tell us about monadic versus adjoint decomposition.
Okay, first of all, let me say that I'm very happy to be here and have the opportunity to speak about these results in this very nice meeting. This is based on a joint work with Claudia Menini, which is on archive. I would like to start from an example that motivated our research. So consider the category of bialgebras where base field K fixed and the category of vector spaces. They are linked by an adjunction where the right adjoint is the primitive functor that takes a bialgebra and maps it to its subspace of primitive elements. So those elements in B whose image via comultiplication is 1 tensor B plus the B tensor 1. It has a left adjoint, which is the tensor algebra functor, and it works as usual. It takes a vector space and it maps it to this direct sum, which is well known to be an algebra, and it is also a bialgebra where the multiplication is defined in order to be primitive on the elements of B. We can also give explicitly the unit and the co-unit of this adjunction. The point is that the primitive elements in T comes out to be homogeneous, and the degree 1 part is exactly concentrated in B. I mean, it is equal to V, and it is a direct sum of pieces, so V embeds in it. On the other hand, the co-unit takes a homogeneous element here, so a tensor product of primitive elements, and maps it to the product of these elements with the product in B. So this gives an element in B, and we have the co-unit. So we are in particular interested in the Eilenberg-Moore construction attached to this adjunction. So as usual, we want to attach a monad to an adjunction. In this case, the monad is this one. And we can consider, as I said, the Eilenberg-Moore category of algebras over it. We denote it by vec1, thinking at vec as a 0 step. And then we denote by P1 the comparison functor that can be defined always in this case. So what happens is that we have a new diagram, and P factors as the composition of the forgetful functor by the comparison one. I denote here the forgetful by U01, as I said, thinking at back as 0, and here you have back 1. What happens is that the category of bialgebras has coequalizers, and we know this is enough to construct a left adjoint of the comparison functor. We can give it explicitly. Take an element in an object in the Eilenberg-Moore category, so it's an object in back. It's a vector space with a linear map mu from PT of V to V, subject to the usual equalities. And what is the image of this adjoint on such an object? It is the coequalizer of this pair of morphisms, that can coequalizer in bialgebra, that can be expressed explicitly as this quotient of the tensor algebra by this two-sided ideal depending on mu. So we have a left adjoint, but now that we have a left adjoint, we can repeat the procedure and consider the Eilenberg-Moore category associated to the monad of this adjunction and call it vec2. So we can add a piece to the picture, and here it is. But again, the category is the same. We have coequalizers, and so the comparison functor, which is P2 now, has a left adjoint. What is nice in this particular example is that it is not any functor, but it can be expressed at this step as the composition of T1 by the forgetful functor, and moreover, it is fully faithful. The fully faithfulness guarantees that if we try to repeat the step, the next forgetful functor will be a category isomorphism. And so in some sense, the process stops after 2 steps, meaning that going on, we just get the same thing, the same adjunction and the same categories beyond. Clearly, I can try to repeat the same idea, starting from a different adjunction. In fact, from any adjunction where the starting category has coequalizers in order to have the possibility to construct the left adjoint. Even less, indeed, is necessary. You don't need all coequalizers, but here you have all of them, so it's nice. If the process, in the general case, stops exactly after n steps, then R is said to have monadic decomposition of length n. This is a known notion, and interesting results on it can be found in the paper that you can see here. In the case of our example, not in the general case, we can give a better description of the final adjunction we get. Indeed, we can construct explicitly an equivalence that we call here lambda from this back 2 and this category Lie, which in characteristic 0 is just the category of Lie algebras, and in finite characteristic is the finite characteristic part of it, so it's the category of restricted Lie algebras. Lambda transform P2 in the primitive functor, the usual one that take a bialgebra and maps it to the Lie algebra of its primitive elements, and the left adjoint comes out to be the universal enveloping algebra, at least in characteristic 0, and the restricted one in finite characteristic. So this process gives you back the usual adjunction between bialgebras and Lie algebras. So in some sense, it permits to recover Lie algebras in this way by repeating the procedure. These results about this particular adjunction have been obtained in several steps in these papers that are joint works with Gomes Torresillas, Claudia Menini, and Isar Goivaerts. If we give a closer inspection of the proof, we can see that the fact that the functor T2 is fully faithful, which is the key point in the fact that the process stops at level 2, follows from a property of the previous adjunction, the junction T1P1. And this property is that it is an idempotent adjunction. This means that the associated monad is idempotent, its multiplication is invertible. And this can be characterized by saying that this natural transformation is invertible. This is the forgetful functor, and eta 1 is just the unit of this adjunction. Moreover, the proof tells that the invertibility of this natural transformation comes from the invertibility of another natural transformation that you can see here. What is, well, U01 is the starting forgetful functor. Eta 1 is the same unit, but now gamma 1 is a new functor. It's a new functor that you can find here and is constructed this way around. It goes the other way around with respect to the forgetful functor, and composite with the forgetful functor gives the identity. I mean, EU composite gamma is the identity. It maps a vector space to a pair consisting of the same vector space and this morphism, which is nothing but the projection of the primitive onto V. I told you that V is part of the description of the primitive element of T of V, is a direct summand of it, so we can project on it canonically. And this projection gives this functor. This is the point, the key point in proving that the adjunction is idempotent. So if one wants to extend this kind of result, one has to put attention to such a kind of functor. The next idea is, okay, what happens if we replace back by any braided monoidal category, and instead of bialgebras over K, we take bialgebras bimonoids in M? Well, let's look at the problem from a general point of view of an arbitrary adjunction. the point is that in general, we are not sure that the process stops, not only after 2 steps, but at all. So gamma 1, maybe it is not enough. Maybe we need to construct more functors in order to attack the problem in a more general setting. And so we would like to construct a family of functors from B to Bn, one for each natural number. The problem is that a first attempt to directly define such a family of functors shows it is inconvenient to prove that the candidate object that we have in mind belongs to Bn. The point is that Bn is an iterated Eilenberg-Moore category, and we know that just at level B1, being here means an object in B with a morphism that fulfills 2 equalities. An object here is a pair of an object in B1 and a morphism with other 2 equalities, and going on, the number of equalities grows. So it's not so easy. And this led to the notion of adjoint decomposition in order to make the problem more handleable, say. So what is it? The point is to substitute the category Bn by a new category, Bn by square brackets, that we could, and with a kind of monadic decomposition that will be called adjoint decomposition. All these guys are adjoint pairs. These are forgetful functors as in the previous case, but what we are doing is trying to forget all the equalities we have to check. So what is an object in Bn? It's still a pair of an object in the previous step, Bn minus 1, but now Bn minus 1 small b n is no longer a map in the previous category, but is a morphism in the starting category. It's morphism from Rln minus 1 of Bn minus 1 to the forgetting version of Bn minus 1. So it's morphism in B. And we don't ask any compatibility, any requirement on B. We can rearrange the datum and split the Bn minus 1 in 2 elements and going on this way. And what we finally get is an object in B, B0, and a collection of morphisms. The first one from RL B0 to B0. Then you can call B1 to be B0 together with the map small b0. And the next morphism is RL1 B1 to B0, and you go on this way. This is a category. We can define in a natural way the morphisms. But what is important here is that we can connect the starting iterated construction with the new one by a fully faithful functor, which makes commutative the solid faces of this diagram. So the right adjoint commutes with lambda n composite Rn is Rn with square brackets, lambda n commutes with the forgetful functors. The nice property, another property that lambda n has is a compatibility with the left adjoint. And now we no longer have the identity, but we have a natural isomorphism. But I was saying the main property that will help us in doing what we are trying to do, so to define the family of functors gamma, is the following one. If the forgetful functor un from Bn to B, it's the composition of this one up to the level 0. If this maps a morphism of this form to a mono, then the source of this morphism must belong to the image of lambda. So it's a way to check that some object is in the image of lambda. We will be back on this property later. I just recall here the notion of augmentation for a monad is just the analog of the notion of augmentation for an algebra. So it's a natural transformation from the monad to the identity, which is compatible in this way with respect to unit and multiplication. And we can state a result that helps us in the direction of constructing gamma. So assume we have a diagram of this form, where LR and L prime R prime are two adjunctions connected by a functor F such that F composite L is L prime. What we need is that the adjunction on the right has a monad endowed with an augmentation gamma prime. And other two conditions. The first is that A has coequalizers and which are preserved by the functor F, and we know why we need A to have coequalizers in order to have the repeated procedure, I mean. And R prime should preserve regular epi and some kind of coequalizer of suitable pairs that you can find here. So if we are in such a setting, then we can provide a family of functors, but they go just in Bn with square brackets. And they are also endowed with a family of natural transformations that help us to write explicitly this gamma n. Indeed, B0 is just B, so we can take a gamma n to be the identity. And gamma 0 should be something from RL identity to identity. So what we are going to pick is just a new augmentation, this one, which is obtained composing the starting one by this natural transformation, which is nothing but a monad morphism between the two monads associated to these adjunctions. And now we can write gamma n plus 1 for n greater or equal to 0. It's just a pair obtained by taking gamma n of an object B and this natural transformation evaluated on B. Furthermore, we have this compatibility condition between gamma and eta, which is the unit of the adjunction Ln Rn on this category. I copy this compatibility condition on the next slide, and I observe that if you just look to this part, eta n gamma n, and you evaluate it on an object in the domain of gamma n, you get a morphism from this guy to this, and this can be written, since lambda n Rn is just Rn with square brackets, can be written as this object. What does it tell, this equality? It tells that the forgetful functor applied to this morphism gives you a split monomorphism, splitting via gamma. Now we recall the property of the functor we defined before, and it was like that. If we have a morphism of this form and the forgetful functor maps it to a monomorphism, then the source is in the image of lambda. And this is the case. This is the morphism. It goes in something which is lambda of something else. It is mapped by the forgetful functor to a split mono. And so we are sure that its source lives in the image of lambda n. Here it is. So this is what we need to restrict the functor gamma n given by the main theorem we have just shown to a functor which goes that goes in Bn. And we have our family of functors as desired in this situation. So now we look for an example where this applies. And this example is given by taking an additive braided monoidal category endowed with both equalizers and coequalizers, and the numerable coproducts. And the tensor products functors, I mean, if you take an object X and if you consider the functor X tensor something or something tensor X, these two functors should be compatible with all these structures. So they are required to be additive and to preserve equalizers, coequalizers, and the numerable coproducts. So in this case, we have a diagram that fulfills the conditions of our main theorem. Some of these conditions are required just to write down this adjunction. We need the numerable coproducts to write to the tensor algebra. We need the equalizers to write the primitive functors as an equalizers, and so on. So what is the other part of the diagram? Alge plus of M is just the category consisting of monoids algebras in M, endowed with an augmentation, so an algebra map into the identity. T plus is just the composition of the forgetful functor with the tensor algebra. Here, note any bialgebra is an augmented algebra via the co-unit. And it has a right adjoint, which takes an augmented algebra, so a datum of this form, and maps it to the kernel of the augmentation, so this guy. And so in this setting, just with these conditions, we have, by applying the theorem, and the results we have seen, we have a family of functors as we want. So what we can do now with these functors? First, compose gamma n with the left adjoint appearing here. So you get T1 gamma 1, T2 gamma 2. Each one of these is a functor from M to bialge M. It will be called the n-symmetric functor. The terminology is due to the fact that in case of vector spaces S1, so this one, in characteristic 0 is just a symmetric algebra functor. So this is a sort of extension of this idea. Let's look at what is this family of new functors, the symmetric one, I mean, in a particular case. Take a finite dimensional of algebra and consider the category of Pieter-Drinfeld modules over it. These are just H modules, left H modules, which are also left H comodules, and the two structures are suitably compatible. Then, if we set S0 to be just a tensor algebra, we can write down as n plus 1, the functor as before, on any object V in Pieter-Drinfeld as a quotient of the previous symmetric functor by the two-sided ideal generated by the primitive elements in Sn of V, which are homogeneous and of degree greater or equal to 2. So you can give it explicitly if we can compute these primitive elements. And each Sn is a quotient of the previous S. So we have a direct system of bialgebras in M, so in the category of Pieter-Drinfeld modules. They are braided bialgebras. And we can compute the direct limit of this guy. This direct limit comes out to be well known, comes out to be the so-called Nichols algebra, which has a relevant role in the study of the classification of finite dimensional of algebras. There is a notion of rank, which is this one. If there exists a smallest n such that the projection of Sn to Sn plus 1 on an object V is bijective, then V is said to have a combinatorial rank n. This is a notion due to Harchenko, and we will write rank of V equal n in this case. Otherwise, it can be infinite. Some facts about these notions, and just to conclude, say, if you take any Pieter-Drinfeld module, the corresponding rank may be as big as desired, even infinite. This is due to Harchenko. And also a question due to Harchenko is whether in case V is finite dimensional, we can say if the rank is finite. We cannot, I mean, it is not known. But we can say something about the rank less or equal to 1. This is equivalent to this condition. This one is exactly the natural transformation we were looking for at the very beginning, when we said that T1 P1 is idempotent because of the invertibility of this red morphism. So this invertibility gives that the rank of any vector space is less or equal to 1. And this idempotency gives monadic decomposition of length at most 2. So we have a connection between rank and monadic decomposition. If we want, this motivates the interest to define a rank in the general case of LR with A with equalizers in the main setting of the main theorem. And what we can prove in general is that the nth step of the process is idempotent for some n, then all objects in B have rank less or equal to n. About the converse, we don't know. It's still an open problem we have to consider. We have an example where we can apply this proposition. In characteristic 0, the category of H modules, in case this is symmetric, so H is triangular, fulfills this condition for n equal 1. And so every object here has combinatorial rank at most 1. So this is what I was going to say. I would like really to thank you for your attention. That's it.
Do we have any questions? Comments? Anyone online with a hand raised? Okay.
I don't hear.
I haven't spoken yet. So this is reminiscent of the problem of taking an adjunction and making it monadic and then comonadic and then monadic and comonadic. And people who hadn't bothered to think about the problem thought this went on forever. And then Steve Lack actually did it and showed that it terminates after 3 steps, of which the third only adds idempotence. Are you sure that this doesn't happen with your problem? I'm not sure that you gave us examples to show that this process goes on arbitrarily long.
You mean idempotency? Yeah, I said that it is idempotency that guarantees the fact that it stops.
Reiteration, is it necessary to go on forever? Or are you sure that you don't?
No. It can go forever. I mean, in principle, it can go forever. For Fourier-Drinfeld models, it doesn't stop after a finite number of steps, for example. So idempotency is not guaranteed, and it's of interest to understand when this is true or not.
Right. When it does terminate, do you end up with a decomposition of an adjunction into a monadic and a comonadic part, or what's the neat version at the end?
The final, it is unknown for the moment, as far as I know. I can tell what it is in this particular case, and the idea here was just to try to give more tools to study it, but it is just at the beginning. Say.
Okay, thank you.
Thank you for your question.
Okay. There are no more questions. Let's thank Alessandro again.
Thank you.